Hello community, welcome to AI Robotics 4. Now in this fourth video, what are we talking about? We are talking about using the intelligence of our ChatGPT, of our large language model, combine it with a real-time vision transformer system and put the whole system into a robot so we can interact with our environment. A real interaction, not just words that you see on your screen, but machines that do something in our world. So, we are talking here about learning robot policies to solve large language condition tasks from vision input. And I thought, hey, why not call simply this new chapter here policy? It is Robotics Policy. If you want to be more specific, here you see a definition what a policy is, but based on our other models, I just wanted to tell you, hey, the RT2 model is fine-tuned to act as a generalizable and semantically aware robotic policy. And I wanted to talk with you about multi-agent non-Markovian rewards in AI robotics. But something happened. In one of my last videos, this was the video, I showed you here a specific research paper. And in this research paper, you see here that right next here to our different LLM system, we have the base model, like GPT 3.5 or GPT 4. And then we always have here reinforcement learning from human feedback. And I received a lot of questions, hey, do we always have this reinforcement learning? What is it? And why is it almost with any model that we see now? So before we talk about robotic policies, we have to talk here about this reinforcement learning based here so that we can use it then for our new robotic policy. So first question, is this for all fine-tuned AI system? What is the function of it? So therefore I call now AI Robotics 4 reinforcement learning. So what is it? It allows our large language model and our vision model and our robotics model to interact with a real world environment. You could also have a simulation, you can have a game, and it learns from the feedback it gets in the form of rewards or penalties. So our language model, vision model, transformer model learns to make decisions that maximize a certain reward. So let's start from the very beginning. What do we have? We have an empty transformer model, and we have a huge data set for pre-training. Let's say we have here the complete internet. So in the pre-training phase here, we combine here, or we pre-train here our transformer model with this data set, and we create here our pre-trained model. Our pre-trained model costs quite a lot of money. It is, to give you an idea, for huge domains like ChatGPT, minimum $1 million. If you have a smaller domain like medicine or physics or finance, you could be up and running for about $100,000 if you do the pre-training and you have the data available. If you decide you want a better performance system that is fine-tuned for a particular downstream task, you find yourself a dataset for this particular task to fine-tune it further. You do the fine-tuning and you end up with a fine-tuned model that knows everything about the internet, has been fine-tuned on your specific task, and now we have a fine-tuned model. And you might say, okay, what about reinforcement learning? Well, imagine you want to further optimize now your fine-tuned model for a certain behavior of your fine-tuned model. Now, think about ChatGPT. You've heard that at the very beginning of ChatGPT, it had also positive and negative statements in its answer to the query. If you want now to train a certain behavior that the system is only nice and friendly when ChatGPT answers, you have to train your system here, your fine-tuned model, for a certain behavior. And this is exactly what reinforcement learning, you want to reinforce a certain behavior on your system. So what you need is here, you have your model, you need a second model, a different model. This model has one function, it gives you a reward. It tells you if it gets an input from the fine-tuned model, let's say a sentence, tells you, hey, this is a positive sentence or this is a negative sentence. So the reward is either, you can have a binary, plus, minus, good, bad, or whatever you like. So you have here two models. And of course, those two models have to interact in a certain way. So let's look at the reward model. Context of reinforcement learning, a model that provides feedback or rewards to the agent. This is our fine-tuned model that we want to further train based on the action it takes. I explain what is an action in a second. The purpose of the reward model is to guide the learning process of the complete agent. So, in reinforcement learning, an agent interacts with an environment by taking action, and for each action, it receives a reward from the environment, good, bad. The goal of the agent is now to learn a specific policy, which is a strategy of choosing specific action that maximize the sum of the rewards over time. This is it. So if you're training a language model to generate text, the next word, it is not obvious how to assign a reward to each generated word or each generated sentence. This is here where our reward model come in. Let's have a look at this. Now, a reward model is trained to predict the reward for a given state-action pair. In the case of our language model, the state might be the current text, and the action might be the next word in the text that the system is generating. And the reward might be a measure how good the generated new text fits to the other part of the text. So once the reward model is trained, it can also be a transformer model, it can be used to provide rewards to the agent during or by the reinforcement learning process. And then the agent, our base model, uses this reward to update its policy and improve its overall system performance on a specific task. Beautiful. Now we know what is a reward model, abstract. Think about it in a mathematical way. It is a function, a reward function for the system behavior you want to achieve. And you get an evaluation, positive or negative, in the simplest way. Now, easy example. Look here at this dog. If you train him to watch here when your LLMs is training and to bark if the training finishes, the reward would be a little piece of meat or something. So your reward is always specific to the task that you ask for. Another example of a reward model. The mathematical function here for NVIDIA is maximize the corporate profit for the global player. And now we might say we have two options. Either my action is I have now a further optimization of my gaming GPUs like RTX 4090, where my profit function is about 90%, or my second option, my second action would be I optimize or I focus my company on data center AI GPUs, the H100 GPU, for example, where my profit margin is about 1200%. So, given your overall mathematical reward function that you defined, that you want the system to behave, you want NVIDIA to be a for-profit company, and you have two actions that the system can act on. You say, to maximize my profit, should I act on option number 1 or on option number 2? So you see, The reward function and the reward model define the complete behavior of the system and defines also the next action of the system if we think about a sequence. And then we have time series, multi-agent, and so on. Of course, that we do not go simply with one action, but we want to have a normal distribution of a multitude of action. But you can see here if you want to maximize your profit, and you have here, for example, the option to go for a data center, AI GPU with a very high profit margin, where is your highest probability. So we have our fine-tuned model, we have our reward model, and now somehow, miraculously, we have to bring the reward back so that the model learns, that the model optimizes. Our fine-tuned model goes to stage 2 with reinforcement learning. How does it do this? Well, it's easy. It is a transformer model. So you know what's happening. We modify, we further adapt, we optimize here the weight tensor of our transformer architecture, of our model, of our fine-tuned model for a certain behavior. And this certain behavior, we have the numerical values from our reward model. If we know this is the positive trajectory and this is the negative trajectory. So this is all there is to it. So once we have the base model, which has been fine-tuned using supervised learning, as I showed you, and a second model, a reward model, could be a BERT model, the next step is to use now the reinforcement learning algorithm to further optimize the base model. You notice this is PPO, the proximal policy optimization comes into play here in the context here, for example, of transformer reinforcement learning, and you have seen TRL. So, two terms I would like to explain. Policy rollout. I was asked what is a policy rollout. Now, the base model, the fine-tuned model, also known as the policy as reinforcement learning terms, it generates an action. As I showed you, it generates the next word in a sentence, for example. So in the context of a language model, action, generate a word, generate the next sentence, or whatever. The reward calculation, now you know what is a reward, and you can imagine how we calculate this. The generated actions are then passed from our base model to the reward model, and the reward model calculates now on this a specific reward function, a numerical value or a binary for the reward for each action. And the reward simply is a measure of how well the action aligns with the desired outcome. If I showed you NVIDIA wants to optimize its profit, you know which action it will support. What is a policy optimization? The rewards are then used, as I showed you, to update the base model. So the goal is to adjust the model's parameter in a way that increases the expected sum of rewards, the overall reward over a certain time period. And PPO as an algorithm can be used for this optimization. So you know statistics, optimization steps, you know where we are. You repeat it, you have several iterations, and the system converges. Of course, we can code this, and code it is even easier. Look, here is the homepage from Hugging Face for Transformer Reinforcement Learning. And if you go there, you see they just give you the code for 3 steps. Now, what are those steps? You have here a supervised fine-tuning trainer module, a script. You have the reward trainer, and you have your PPO trainer. And now you already know what it is. This here, our supervised fine-tuning trainer, is simply that we fine-tune our model with a data set. This is it. You take, for example, a specific model that's available, Hugging Face, Facebook here. You have a training data set, and you define a sequence length, and you do the normal fine-tuning of a model. As I told you, you have the base model, then you need the reward model. Now, if it's not just a function, but it can be also a transformer, a neural network in general. So you need to train this model. So you have a specific model and you have training data. You have a data set that trains, for example, let's say it's a bird model, and you have a movie review. Then you have a positive connotation with a sentence or a negative connotation. This movie was beautiful. This movie was horrible. Positive, negative. You train now this reward model. And then you combine it and you simply have here a PPO trainer. What you do? Easy. You have here your base model that generates here a response. You forward this response here to my reward model. I get the reward back. This is good, this is bad. And then you have here the trainer. You train now the PPO trainer with the query, with the response, and the reward. And with those three parameters, you are now in a position here to further optimize here your supervised fine-tuning model using the rewards from the reward model, applying the PPO algorithm. Here you have again in text. If you want to see this in action, this is easy. This is what I showed you before. The pre-trained model and the fine-tuning, and then here our supervised fine-tuning trainer script here, those lines here, create the fine-tuned model. This is it, what we do every day. Then, as I told you, we have here a model that calculates the reward, that predicts the reward if the model has been trained on a lot of data. Then we have here the reward. As I told you, we have here now the next word, the next sentence is generated by our system. We forward it here to the reward system. We calculate the specific reward. It is positive, the movie, or it's a negative movie. And then somehow we want to feed this reward back to optimize here our base model. This is all there is. So optimize mean our fine-tune model. Either you have a lot of practical code possibilities to do this, but normally you adapt here the weight tensor for a certain behavior that comes here back with your reward function. And this is done here, as I showed you, by step 3, your PPO trainer. This is all to it. So if, for example, in the past, let's say this was our ChatGPT, our root version that has positive and negative answers to the US, and you trained then here with reinforcement learning from human feedback, this is another complication I will talk about later. Then you have here the PPO trainer. PPO as an algorithm was developed by OpenAI, so that now here the adapted weight tensor only provide answers to the user in a nice and a friendly way. This is all there is to it. Now, time does not stand still, so there are new methods, new great ideas. So we go from PPO to DPO to direct preference optimization. So PPO is more or less here a thing from the past. And even if you go to Hugging Face, you have here the DPO trainer, an integral part of the code that Hugging Face provides to you online. It's a script, you just call it here. This is the complete code for our DPO trainer. And you can apply now a much more modern algorithm here for the DPO. What else? Yeah, if you want to see a complete code example, this here is the GitHub hub. This is from Van Vera, and you just go to his examples and you look for the file, for the Python file DPO, and there you have the complete code. You can run it, you can play with it, you get yourself familiar with the code. Short interrupt, let's summarize the reward function. The reward function is crucial in reinforcement learning as it quantifies the desirability of different actions, A for a given state, S, A for action, S for state, guiding here the learning process of the complete system. So we want to find out of different actions that are available to the system. The system has a given state S. So what is the state? The state is the temperature, the state is the velocity of the system, the state is the energy of the system. So to all the state parameters that we have on a robotic system, for example, we have different actions. An action could be move the arm forward, move the arm backwards, right, left, up, down, whatever you see. For a specific goal, you want to train this with a learning process. The policy. The policy, think about policy about the strategy that the agent, our base model, uses to decide what of the multiple of action a robot arm can move, what action should it take? Move straight forward for a certain amount of space. So in reinforcement learning, a policy is a mapping from the states to the actions. The goal is to find the optimal policy that maximizes the cumulative reward function. And this often involves learning a function that can accurately predict the expected reward for each possible action in each state of the system. So you see, you want to find here the best way forward for the system to achieve the given task. Now, the beauty is that transformers can be used to learn this function. And transformers can be used to optimize a policy in reinforcement learning. So the transformer's ability to handle here sequential data, words in a sentence, and model long-term dependencies makes it well suited for policy optimization tasks. The example is you have a little robot to navigate a maze. And here I will introduce here the notion of non-Markovian rewards. The transformer architecture here is particularly good here with non-Markovian rewards, which are characterized by delays and dependencies on the sequence of states encountered during an episode. For example, when the reward is only provided at the end. Let's say you have a mouse in a maze, and somewhere in the maze there's a little bit of a cheese, and whenever the mouse finds the way to the cheese, the reward is the cheese is only provided at the end when the mouse found the solution, the right path to the cheese. As easy as that. Yeah, a Markov decision process, interesting. It is very simple from the idea. If you say that the future states of the environment of a system can be predicted based only on the current state, without any knowledge of the past state, so you say the current state defines the complete future, then we have here Markov decision processes. However, if this is not the case, we are talking about non-Markovian rewards. So this means that the reward at a given time step could depend on the actions taken or the states encountered at previous time step. Now, think about here again the mouse or the robot navigating a maze to find a piece of cheese. If the cheese is located at the end of a specific sequence of ways how to run in the corridors, the robot might receive the reward only when it reaches the cheese. You see, it depends on the sequence of correct actions. First left, then right, then straight on, then 2 times left. So this sequence of action that bring you to your goal. And the reward is non-Markovian because it depends on the entire sequence of action, not just the current action or state. And here, in the non-Markovian reward system, we have architectures like the transformers who are just working great. If you want to learn more about transformers in reinforcement learning, there's a very good survey here, July 12, 2023. This is the archive. Go have a look at this report. This is the principal schema that they explore, and they look at all the different options that there are. You can see here the different authors. You find the link in the original paper where you have an agent in a specific state. The agent now starts an action. The action has an imprint on the environment. You have a reward function that defined if this was a positive or a negative action, if the agent wants to continue with this action or wants to take a counter action. They run through this and they give you all the different models and papers and theories. Really interesting paper. So, as I told you, transformers, we do not use transformers only for a large language model and only for vision transformers, but we have it also in robotic transformers. And this is because they are amazing. Let's have a look even in the topic of policy learning, what they can do. And I give you 4 examples. Robotics, graph-based reinforcement learning, story generation. This is what you do with ChatGPT. You write a science fiction story. Or you have decision transformers. In all of these cases, you have a policy learning. Now let's look at robotics. Learning the reinforcement learning policy for a trajectory planning is essential in robotics. Either the arm has to move or the robot itself has to move, so you have to have a planning for the trajectory. Transformers have been used for processing sequences of high-dimensional scene observation for predicting actions. For instance, uses vision transformer to extract spatial representation from a bird's eye view on a vehicle to learn driving policies. This is what Tesla is doing with its Dojo chip. But Tesla is restricted to a 2-dimensional sphere. You do not have that you can suddenly fly up in the sky or something, and you have fixed objects that you identify. Think about you want to drive a Tesla car on Mars. You can't because the object on Mars are for the system unidentifiable, so the car will have no ability to do this. But in a combination with robotics, you can learn robotics on unseen objects. Beautiful, beautiful. So navigation task, path planning, navigation, this is great. You have another way, this is just I want to introduce you, graph structure. I have a lot of videos about graph neural networks, and here transformer are bridging here those 2 topics, because think about this. In many robotics applications, the environment or the problem itself can be presented as a graph, where nodes represent the different states or the different location of a robot, and edges represent possible transaction between them. To give you an easy example, each room in a building could be a node, and the doors connecting the different rooms could be the edges. So you see, you could simply from the map of a skyscraper create here a graph that a transformer would understand. So this topological structure refers now to the arrangement of nodes and edges, and we have a graph-specific representation that I have a lot of videos about how to do this. But the beautiful is we can use this structure for decision making in reinforcement learning tasks with transformers, because transformers can be used to process these graph structures. And this is something really, really beautiful. But robots for manipulation tasks. Showed you the videos, a transformer used in robotics, picking up some chips or assembling some parts or moving object from one corner of the desk to the other corner. But of course, if you think a little bit more complex, if you think about, as I told you, you have a spacecraft in the atmosphere of Jupiter, multi-agent system. Transformers can be used also in multi-agent systems, where multiple robots or multiple systems, agent, base models, LLMs, LiDAR, radar, visual data systems need to coordinate their action to achieve a common goal. And here, the ability of a transformer is you take in all the current state of all the different agents and you output a distribution of possible actions for each agent. And the transformer can be trained to adjust this distribution to favor specific actions that lead to the successful completion of a task. So for example, in Jupiter's atmosphere, suddenly our spacecraft has to switch from visual sensors to infrared sensors or to any other sensory array, combine the information from different sensors, and come to a conclusion what is the object that is right in front of in the path. So, in all these cases, the transformer can be used to learn an optimal policy that maximizes the expected cumulative reward for the system. And this is the beauty. Now, how do we do this training of a transformer in a multi-agent system? It is as simple as it could be. You have an input representation, this is your input. You have the model itself with its architecture. And as I told you, if you have a model and we do RL, we need also a reward model or a reward function. So these are our, if you want a recipe, our three main ingredients. First step, represent the current states of all the agents in a way that can be processed by a transformer. Involve encoding each agent's state into a vector. You know, vector embedding, the vector store we do if we read in a PDF file, for example, to ChatGPT. And then we concatenate those vectors into a sequence, or we perform certain specific mathematical operation with multiple vectors. We build different complexity in vector spaces. If the actions of other agents are also considered, they can be included in this state representation. Here really your fantasy is the limit of the performance. Now the model itself takes the sequence of state representation as an input. It processes the sequences. You remember I showed you the token. We had at first, for example, a language token, then we had the vision token, and then we had the robot actuator tokens. We process this sequence of tokens using the self-attention mechanism feed forward, which allow the model the relations between different agent state. And then you define a reward function to evaluate the quality of all the different actions taken by all the different agents, and you calculate the specific set of agents to achieve your goal. Now, the training algorithm is, again, as I showed you, trained using a reinforcement learning algorithm like PPO or any suited optimization. The goal of the training algorithm is to adjust the parameter of the transformers to maximize the expected cumulative reward, as always. Interestingly here, there is now a balance between exploration and exploitation. So during the training, you need to have here this sensitive balance between trying out completely new action to discover completely new path forwards for better strategies, or you stick with the currently best known actions and you are only allowing it to deviate a tiny little amount from the known best action, thereby limiting yourself from finding complete different ways that might lead to a significant better performance. So given the amount of money that you want to invest here in the training, this balance between exploration and exploitation is really something you have to fine-tune yourself. You say, hey, I want to stick to the known actions, or you say, hey, I'm courageous, I'm brave. I try out completely new action. I want to see here if I have an action manifold, an action space, continuous or discretized manifolds, how many paths forward there are for my systems. And then you have the training loop, and you do again and again and again till you reached here a satisfactory level. Great! Now this was the interrupt about reinforcement learning with an eye to our AI robotics, and now the next video will be AI robotics 5 and finally I can show you here the mathematical definitions and the real formal structures to define robotic policies. I hope to see you in my next video.